No, it's really fine. Yeah. All right. So the last speaker of the session is Christos Thrampoulidis, and he will speak on the implicit geometry of semantics in NTP models.
Good, thank you. All right, good. Thank you very much to the organizers for the invitation and for putting together such a nice workshop. So yeah, I will talk about some of recent work of the group on trying to understand the way that large language models represent information that is given to them during training, and this is joint work with Implicit and Vala for students at BBC. Okay, so to get things started. All right, so no much motivation needed. I think we all in this room agree various extents that LLMs do understand language. And I guess what I personally, and I'm sure many of you share, and find interesting is that they don't understand language only in the form of explicit meaning, but they do understand more complex meaning. And so here's an example of what is known as semantic fields in linguistics. So these models do understand the relationships between concepts, between linguistic objects that might not be synonymous to each other, but relate in terms of semantics. So here is just a demonstration of this, where I don't know how much you can see, but I'm just asking Claude to whether it understands the semantic field of happiness. And what it demonstrates here, it recognizes that things like joy, but also smile and laugh and celebrate, that are not directly synonymous to each other, but they all relate to this semantic field. And kind of the high-level question is, how did this model learn this? Now, in order to answer such a question, perhaps we can go back to what are the key ingredients of LLMs, and perhaps we can put those in three brackets. So the first one is clearly the architecture. The transformer architecture has enabled scaling the models to order of trillions of parameters. Recently, though, there have been suggestions for potential modifications to the architecture. We already listened to some suggestions in the first talk during the day, but I think undoubtedly transformer has been the go-to architecture. Now, the second ingredient is the way that we train these models. And the standard pre-training method is that of using the next token prediction objective. And you're doing that on order of trillions of thousands of data sets. And after pre-training, there's this post-training phases that again has different variants. And so what I would want to do in this talk is focus on this second ingredient, which is the next token prediction. And probably I don't need to remind you much of what next token prediction is. We heard a lot about it yesterday, but just to be on the same page and set up my terminology of things, here's an example. So I'm giving to the model a context, which is a sequence of words or tokens. I'll be using words and tokens interchangeably. So the context is Canada is famous for each. It goes through the embedding map, it gets mapped into a d-dimensional representation. And this d-dimensional vector, now I hit with the d-dimensional representation that I have for every word in the vocabulary. So there's v words in the vocabulary. I get out v logits. I pass these through a softmax map, and I get a probability vector q sub theta. And the way that I train all the parameters of the neural network is by going through the entire data set, going through all the context and trying to minimize the cross entropy loss of the output of the model q sub theta with respect to the one-hot representation of the actual next word that appeared after the specific instantiation of the context in the data. Okay. And so the question is, how does this conceptually very simple mechanism lead to models acquiring complex semantics? Okay, that's kind of the motivating question here. Now, before I tell you anything, just a disclaimer. So I'm not gonna be showing you any state-of-the-art method for extracting semantics. There is other line of works that are much better suited at doing this. And so there's works that are using ideas from dictionary learning or sparse coding or use of sparse variation on autoencoders. And there's methods like probing these models, either with linear models like what we heard from Bachal or with nonlinear models in order to extract semantics. My interest on this is trying to understand more from an optimization viewpoint, how does this objective of next token prediction leads to an emergence of semantics as a consequence of just me doing prediction of the next token. Okay. So that's kind of the high level. And before I even go into talking about semantics that are not explicitly modeled in the training data, I want to look at the explicit training signals of the system. And what is the explicit inputs to the system are the words and the context. Okay? So what I want to understand is how these D-dimensional representations of words and context get arranged in the embedding space. And so just to give a visualization of what I'm hoping to be able to do. So here is the cosine similarities of context embeddings and word embeddings at the end of training a transformer model on a specific data set using the next token prediction objective. So I train my model, and at the end of training, I take all my contexts and I compute cosine similarities of context to context, and I do the same for the words, and I get some structure. Kind of the question is, can I get some prediction of how the structure looks like without having to actually train the model? And so this is what I will try to show you a way to kind of think of this question in the next 15 minutes or so. So there will be three key ingredients. The first one has to do with framing next token prediction. The second one will involve me introducing an assumption of having a sufficiently expressive model. And the third part will be doing an analysis using the technical framework of implicit regularization. Okay. Any questions for the motivation? Okay, good. All right, so let's start with framing next token prediction. I've already talked about this. I'll just put it into mathematical notation, I guess now, really standard things. So I have a vocabulary that has V tokens, and I'm given sequences of words. And every sequence of words, which I call context, gets mapped into a context embedding. I view this mapping as something that maps context to the D-dimensional space, and I denote it as H sub theta. Theta kind of hides all the complexity of the architecture. And then I have a matrix of word embeddings that is V times D, so every row of this matrix is a word embedding. And what I do is I minimize the next token prediction loss, where I go over all context and try to predict the 1/4 representation of the actual next word in the data. Okay, so this is the next token prediction objective. What I want to do in the next slides is I want to rewrite this objective with respect to the unique contexts that appear in the data. Okay. Why do I want to do that? Because when I parse a very large data set, it is very likely that I will see the same context multiple times. And every time that it appears, it might appear with a different token following the specific instantiation. Okay, so for example, the context Canada is famous for it might be followed by different tokens in the data set. Okay, and you know the frequencies that you have for this next tokens might depend on how recently you created your model. Now the second simple observation here is that not all vocabulary tokens are possible next tokens for a specific context. Okay, so for instance, you know, expecting to see something like Canada is famous for its affordability is not something that you expect to see in a data set. And so I'm talking about in support and off support tokens for every given context. Now, maybe one thing that I want to emphasize that this sparsity property is not only a result of finite sampling of the data set, but rather I think of it as an inherent property of natural language, right? So there's some next tokens that will not appear for any specific context in natural language. And so what I'm going to do now is I'm going to rewrite my objective with respect to this distinct context that I'm going to isolate over the all possible contexts that I see in the data set. Each one has some prior probability p hat j, but more importantly, each one is associated with a sparse probabilistic label p hat j that has a support set of size that is much smaller than the size of the vocabulary set. And this is how my objective looks like now, where I'm going through only the distinct contexts and I'm minimizing cross-entropy loss of the model output, which is the softmax of the logits with respect to this sparse probability value. And what I'm trying to do is I'm trying to understand when I optimize this objective, what happens to the weights. Now I cannot do that. The reason I cannot do that is because there's some wild complex architecture that is hiding in this embedding map. So what I'm going to assume that this model is sufficiently expressive so that it can really optimize an embedding for every distinct context in the dataset. Okay, and so I'm going to use this idea of unconstrained features that has been used in various contexts in the literature and recently has been extensively used in the context of neural collapse, which I will come back in a little bit. Okay, so what I've done now is I've turned the next token prediction objective into this bilinear optimization problem where I'm optimizing over a matrix of word embeddings and a matrix of context embeddings, so two matrices. And this is a log bilinear model, right? The logarithm is hiding inside the cross entropy. And the question is, what the geometry solutions W hat and X hat? Okay, so how are we going to approach this? We're going to use this idea of implicit regularization. So we're going to think of this objective as having an additional ridge regularization with some hyperparameter lambda, and we're going to let lambda go to 0. And we're going to ask what happens to the solutions to this optimization as lambda goes to 0. The reason I'm looking into this limit is because I'm thinking of this regularization path as a proxy for the gradient descent path. So I'm thinking of the behavior of the solutions as lambda goes to 0, kind of emulating the behavior of gradient descent iterations as the number of iterations go to infinity. Of course, this is not formal. This equivalence is not formal in this setting. It's has been only formalized in linear settings. So here I'm just using it as a proxy, just because I cannot do the gradient descent. Okay, so here's the first observation. The first observation is that I don't need to worry about analyzing the problem in the WH space, but rather I can look at the logit space. This is a very simple observation. It boils down to recognizing that minimizing the sum of squares of two matrices subject to them being both free essentially reduces to nuclear norm minimization of the product matrix. So now I'm looking at this nuclear norm penalized next token prediction objective, and I know that if I can tell you what the solution to this nuclear norm regularized problem is, then I can just do singular value decomposition, and this will tell me what is the solution to the original problem. Okay, so in that sense, this relaxation is tight.
What are those norms, the W square and H square?
These are Frobenius norms. Yes. So this is ridge regularization. Yes. So these are Frobenius norms. And so if I can solve for the logits, then the left singular vectors up to some rotation is going to tell me what the word embeddings look like. The right singular vectors are going to tell me what the context embeddings look like. So, sorry.
Basically, like something you do this as more like they are Frobenius norms, so more like application of the gradient norm.
Yes.
So you can do that as like really some kind of lower solution. Which means that so the pretty lowering kind of rotation to WH, which is very similar to what we heard yesterday, which is the lowering assumption for the probability, which is after those ones. So
Right.
The question is going to be lowering model.
Yeah. So that's correct. Maybe the thing that I want to emphasize is that, and this is why I call this implicit geometry or implicit solution, because here it's more explicit because it seems like I'm adding this regularization, but kind of what I have in mind is that I'm kind of simulating what gradient descent would do. Gradient descent kind of operates on the Euclidean space with respect to the Euclidean metric. So the regularization that I'm adding here is consistent with gradient descent. Maybe if I was analyzing something like Adam, then maybe here I would penalize with the infinity norm, perhaps. And so this would give a different behavior. So kind of the way I think about it is that the nuclear norm here is implicitly preferred, the low rank structure is implicitly preferred by gradient descent in this specific problem, just because you have this WH factorization. No, there's no minus. Yes, you're right. There's no minus. I had minus initially because I had the cross entropy minus logarithm of the softmax. You're right. Yes, there's no minus. So this problem is actually convex up to this constraint. Okay, and I need this constraint to be able to do the factorization on the d-dimensional embedding. So what I'm going to do is I'm going to get rid of this constraint. So I'm going to assume that d is greater or equal than v. So the dimension is larger than the vocabulary. Now that's a unrealistic assumption for language models, but I claim that it still maintains some interest to the problem. For one, what I'm doing is I'm imposing no constraints on D, the dimension being larger than the number of contexts that you see, right? So still I have a D-dimensional space and I have a huge number of contexts and I want to see how their geometry looks like. And so perhaps I'm simplifying the problem with respect to words. Okay, so under this assumption, here's the claim that as lambda goes to 0, then the logits that are parameterized by lambda are going to decompose into two components. There is a sparse component and there is a low rank component. And as lambda goes to 0, the low rank component becomes dominant. And heuristically writing this means that as lambda goes to 0, and if I were to normalize everything by the norms, then the low rank direction would remain prominent. Now, these sparse components and low rank components, they are orthogonal to each other. Okay? So the sparse component, it has the same sparsity as the sparsity of the data. What is sparsity of the data? For me, I'm looking at this matrix of words versus context, and I think of every column as having one if a specific word appears after the specific context or zero otherwise. Okay? So the data set uses some sparsity matrix, and this sparsity matrix determines the sparsity patterns of this sparse component. But I don't care that much about the sparse component because the dominant component is the low rank one. And this low rank component depends only on the sparsity pattern and not on the frequencies with which the words follow the specific context. Okay, so let me give you the explicit form of this low rank component. It's the solution to an SDP, so that minimizes the nuclear norm of the logits, subject to linear constraints that look like a support vector machines. What I'm trying to do is I'm trying to separate in-support logits from off-support logits and make sure that in-support logits are the same with each other. So this is an SDP that if you have access to what is the support set of each context and not the specific frequencies, then you can solve it, and this gives you the low rank component. I call this low rank because I'm thinking of nuclear norm using a low rank product. Okay, any questions on the statement? I skip the formal version. Okay, now in general, I need to solve this nuclear norm minimization to find what L is, but in some special symmetric cases, we can actually solve in closed form. So here is a special case where my sparsity matrix has V rows and it has V choose K columns, and every context is followed by a specific K subset of the words, and every context is followed by a different K subset of the words. A very, very symmetric scenario. In this case, we can show that the solution to the nuclear norm minimization is just a centered version of the sparsity matrix. All you're doing is you're just centering this matrix with respect to the columns. And in fact, you can actually compute the SVD factors in closed form, and you can actually find the geometry of the words and the context in this scenario. I will not go much into the details. I just want to make a link to something that you might have heard of. So in the special case where K is equal to 1, what does this mean? It means that now I go back to the one hot classification, image classification setting and I'm actually balanced. So I have a fixed number of classes, V classes, and every context belongs to one class, and I have equal number of contexts for every class, then it kind of boils down to the result of neural collapse, right? That said that classifiers and embeddings form an equiangular type frame. So you can think of the result that I showed you previously as an extension of the neural collapse property in the sparse soft label classification set. Now, in general, we do need to solve the SDP. Experimentally, we do find that this centered version of the sparsity matrix is actually a good proxy. And so I'll show you an experiment that this is the case. And so kind of the meta result that I want to think is that if I think of the language model as operating in this doubly asymptotic regime that is very large, very expressive, and is trained very long, so that I emulate what gradient descent does at infinity, then the word embeddings and the context embeddings are left and right singular vectors of the centered data sparsity. That's kind of the meta result here. And so here is an experiment where we're training a transformer model on context, simple context of the form, a little girl named Lily, blah, blah, there was a little boy, blah, blah. We keep a small number of them so that we can actually compute the sparsity matrices. First, we train a transformer model and you look at the correlation, the cosine similarity matrices for embeddings and words at the end of training. This is what I showed in the beginning. And what we want to do is we want to compare this to the theoretical prediction. And in order to do that, we have to construct the sparsity matrix, give it as input to the SDP, solve the SDP, compute the SVD of the solution, and compute the respective cosine similarity matrices. And you can see that this captures the patterns. And if I were to just use my proxy, which is the standard data sparsity matrix, then again, I get pretty good math. What was?
K.
K. So K doesn't appear, it's not one of my main variables. In the previous setting, K was the size of the subset of words that follow a specific context. With a number between 1 and 3. But in general, for every context, there could be a different K. Right? Okay, so now, yes.
So the result and the minimization of cross entropy with that regularization, so that's that it would lead to that decomposition of decomposable logic.
Right.
So that's the main.
Yes.
Right?
The main result is that.
Show that? What is the way to show that?
Yeah, it's not. So this uses that's a good question. So let me maybe show you the formal version of the results so that you get a little to understand what it involves showing. So basically, what you're doing is you identify a subspace, and the subspace looks ugly, but it's just the subspace of matrices that have the same support set as the data, and then you track your parameters as lambda evolves. In their projection to this subspace and the orthogonal subspace. So when you project the iterates on this subspace, basically what you have is you have percent of minimization on a subspace that there exists a finite minimum. And so then it behaves nicely, it's strictly convex, it's going to convert on this subspace, it's going to converge to the minimum, and this minimum is the sparse component. And then on the orthogonal subspace, basically what happens is your data are separable. And so you have to diverge, and what you're proving is you're proving convergence in direction. So this is analogous to the result that says that if you run logistic regression on linearly separable data, then you will converge to the max margin classifier. Here I'm doing the bilinear version, essentially, in a setting where I don't have purely separable data, but my data are only separable on a specific subspace. And they are separable on a specific subspace because the matrix is sparse. This sparsity is what induces this property of diverging norms. Okay. So let's go jump now into semantics, which is a more preliminary work, and so I don't need too much time to talk about it. But I'd love to share any feedback. Okay, so now let's return to semantics and try to understand how is semantic information encoded in this geometry that is induced by the data sparsity. And so kind of the obvious answer here might be, okay, so you know that word embeddings and context embeddings are given by SVD factors of this sparsity matrix. Maybe you should look at these SVD factors for semantic meaning, right? And so let's do that. Here is a setting where you have sentences of the form a subject is an attribute. So subject is my context, and then attribute is the next word. And I'm doing SVD of the centered version of this matrix, and I'm looking at the right singular vectors. And what I told you in the previous part of the talk is that the rows of this singular vector, of this singular matrix, up to some rotation and scaling with the singular values, are going to be the context representation. Instead, what I want to do now is I want to focus on the columns. Okay? And essentially, these columns are the principal components of the data sparsity matrix, right? And the way that I want to interpret every entry of this column is I want to think of it as if it's positive, then it means that the corresponding context is positively associated with the corresponding direction. Otherwise, it's opposed. Okay? And so now what I can see is I can see like a clear splitting of things that are associated to this specific direction, being the fruits and the rest being the animal. Okay? So this is the plant versus animal principal direction. And I might hope that by doing this for all different principal directions, I get semantic meaning. Now, it turns out that this is not the case. Okay, so these principal directions do not have semantic meaning, and this is not something surprising. It's consistent to what people have known about static word embeddings previously, and now it has become popularized as under the name of superposition by people in Anthropic. And so instead, kind of the hypothesis that we have is that you can extract semantic meaning if you look at specific combinations of multiple concepts. And so here's how our specific combinations are going to look like. We're going to take a subset of the concepts, let's say the first, the second, and the 10th. We're going to look at the projection of the context on this three-dimensional space. And then what we're going to do is we're going to start looking at suborthants of this space. Okay, so if I just constrain the first direction to be negative, then I'm looking at a suborthant of dimension 1, and this kind of induces the cluster of all the contexts that represent animals. If I look at the first two directions being both negative, then I look at a subcluster of dimension 2, and this gives me pets, and I can continue and derive dogs and so on. Okay, so kind of what we're suggesting is that if you look at specific signature configurations over multiple concepts, then this gives you an orthant-based clustering that has this hierarchical feature that often will induce semantic meaning. Okay, so here's a demonstration where we keep the vocabulary size small and the number of contexts small so that we can actually construct the data sparsity matrix and do its SVD. And what I'm showing you here is I'm showing you at selected suborthants, the words that are included in this suborthant in terms of their representations. And I'm just plotting this as word clouds where the size of the word represents the typicality with respect to the specific semantic. And so you start seeing that even with this simple data set, I start seeing things such as all past tense verbs or present tense verbs being one cluster, and months and numbers. Now, perhaps disappointing feature here is that these are not exactly what we think as semantic meaning, right? It's more like syntactic and grammar. And so maybe what you're hoping is, okay, if I now scale my data set, then this will induce a rich structure in the sparsity matrix. And so this will induce rich semantics. Now, my problem is I can never construct this sparsity matrix. And so what I will do instead is I will just pretend that the theory previously was correct. And so I'm going to just look at the word embeddings. I'm going to do its SVD, and I'm going to do this type of orthant-based clustering on the first 5 to 7 concepts. And I'm going to look at pre-trained word embeddings from GPT to small. This will be a data set of size 100 tokens. And so now we can find clusters of small dimensions that have more clear semantic meaning. All right, so we have some more experiments here, but I think I will end by just summarizing that we're trying to understand from an optimization viewpoint how prediction of next token induces specific representations of words, contexts, and semantics. And as a starting point in this investigation, we're looking at these models in an asymptotic regime where they're expressive enough and they're trained long enough. And then we're relating them to the centered data sparsity matrix. I think there's many exciting questions here. There's some technical ones, like I think even moving beyond this linear setting of separable data where we fully understand it, we don't really know the gradient descent dynamics in this log bilinear model. I think it's kind of embarrassing, to be honest. Now, in terms of what is missing from the theory, I think really one thing that is missing is capturing a notion of implicit soft labels where the transformer effects will essentially play a role. And I think there's a bunch of questions on semantics. I think I will end here. So can we go for lunch? Thanks again.
Yeah, let's look at the similarity between looking at how you're communicating with certain embedding and more embedding of feeling models.
Best.
When you're showing the first column was one transformer train, but with some facts, but we actually looked at these similar things for the transformer. I mean, not one basically big connector mapping. Most are working by connector and see how they actually consumer the error.
Yeah, my problem is that, so I can compute the logic matrix and kind of the claims that the logic matrix should be the same as this centered data sparsity matrix. I don't know what this centered data sparsity matrix is because I should have access to all the data, and for every context, I should know which next word appeared in the data set. So I would need kind of a huge n-gram over like this huge scale data sets that people train these models on.
But just to limit the, look at the subset of different categories, look at the subset.
Yeah, we can do that, and we have tried to do that. It doesn't match. I think one reason is that really you need to capture the entire data set, because like this you can't just say that like this, like especially when you're talking about SVD factors, right? But it's not a local property. It depends on the entire matrix. I can't just look at a subset of the columns. So that's one reason. I think another fundamental reason is that currently trained LLMs are not trained to interpolate, right? They're not trained long enough and they're not expressive enough. So I do recognize that here is kind of an idealized regime where we are trying to investigate that. I do have more hope though in terms of looking at the semantics. This seems to agree a little more with the orthon-based cluster.
Okay, thank you. Your document similarity problem, like high dimensional things that is not solvable by answering?
Oh, good question. I think the answer is yes, but there's probably, it's like kind of harder to define even these problems about like find triples of documents that are correlated. I think in Daniel's paper, they really do identify a problem called, they call it match 3 or match K, which is kind of answering your question. It's not exactly the same as document similarity, but it's similar to that. Yeah, and it's kind of the motivation of why they defined this in the first place. Yeah.
Does this topographic improvement in closure layers translate to autoregressive decoding something like where you establish linear attention for each token?
Oh, it should let me give you a big answer. Any situation where like there was like invited attention matrix and you can do it faster with a low rank approximation, it should work in all these different settings. Yeah.
So you think like on the positive you are like linear algorithm for the code?
I'm just like
Like when decoding, like you maintain this KV cache like previously, and each time you only want to like do a forward possible like new generate token. The default running time of attention for that is like linear time.
Yeah.
Would expect like this linear time like as a counterpart of like the credit time here.
Good
That's
question.
like multiple can do per time.
Yeah, good question. Yeah, off the top of my head, I'm not sure actually. Yeah, there's not like some straightforward way to combine like the matrix of low rank with KV caches, right? At least not that I know of. I don't know, maybe there's something simple I'm saying. Yeah.
Lower rank, you can, like that's what linear attention does, right? You just shift the thing and then you can have a recurrent version where the quote unquote KV cache is much smaller. So that you track of you.
Oh, so it saves like the space rather
rank
than the time,
so like it's ND and DN, right? And if you make that kernel map of size F, then I think you need to only remember order F or something like that.
Oh, I get
So
it.
you can actually do this recurrent segment slower.
I see. I see. I guess the point is you can view it like linear attention, but the middle thing is not D, it's
It's
the
larger.
bigger thing, but it's still in a little of one. Okay, yeah. Yeah.
So for the weight bound condition, does that basically restrict your attention weights to be kind of diffuse? Like you can never have anything that's too sharp? Is that like an equivalent thing that this is ending up doing?
Roughly, yeah. If there's like a small number of sharp weights, you might be able to separately deal with them, like remove those and then reduce to the small weight setting. If for the hardest to kick in, you really need there to be lots of big weights.
I see. So you get lots of But like it gets normalized by the soft amps, right? This is what I was trying to.
In the attention matrix.
Yeah, right.
I see. Yeah, that's right. I mean, the hardness, that's right. So like the hardness ends up saying there's like in the attention matrix, there's like n bigger entries and like the hard part is finding those entries. So
Got it.
yeah, it's exactly like you're saying.
So it's just kind of saying, like, another way to interpret this would be to say, like, instead of like thinking about the attention matrix, thinking about like the actual underlying problem. If you have a problem where you're doing like n sparse retrievals, then you shouldn't expect good performance out of a linear time model. Is that like roughly a?
Yeah,
I want to say.
I think that's right, yeah. Yeah. Yeah, you should all learn fine-grained complexity, it's very helpful.
What is it called, fine grained?
It's because like the goal is to prove finer grained hardness statements that like traditional complexity is able to prove. Like n versus n squared, it's not just a polynomial, it's not. Yeah.